Hello everybody, these are some problems that are related to survival analysis. So I have three different problems, we're going to go over all of them. The first problem is set up kind of interestingly, so I'm just going to go with it and I'll explain it as I go on. So we have 430 individuals receive treatment for disease D, whatever that disease is. What's the probability one survives 3 years post-treatment? So in order to survive 3 years, they have to survive year 1 and year 2 and year 3. Anytime you hear and, A-N-D, and in relation to probability, you should think of multiplication. And means multiplication when it comes to probabilities, or means addition. So here we have an and situation. So we will be multiplying probabilities at some time. You can hear a lot of cars passing by. I live in a busy area. There's a lot of cars here. All right, so we have a very specific situation where we're starting at 2014. We have 5 years. We have a total of 430 individuals receiving treatment. Some of them are in this study for 3 years. Like those, well, we're only following these individuals for 3 years, but we have 5 years worth of individuals here. So the first 100 individuals came in 2014, and they were followed for 3 years, right? The second group of individuals came in 2015. There were 90 there, and they were followed for 3 years as well. Third group was followed for 3 years as well. The fourth group was followed for 2 years, and the last group was only followed for 1 year. So we have a total of 430 individuals. So let's start by calculating the probability of surviving 1 year. So we know that everybody in this study was in the study at least 1 year. So we have data that covers at least 1 year, going from the initiation of treatment to 1 year post baseline. Baseline is when we initiated the treatment. So we have a total of 430 individuals, and 270 of them survived 1 year. So if we want to know what the probability of surviving 1 year is, we need to divide 270 by 430, and that's what I do here. So this is the probability that one survives 1 year. It's very simple, right? That's just a ratio, right? Now we want to know what's the probability of surviving 2 years given, so this is a conditional probability, there's a condition here, given that one survived 1 year. So let's go back to the data here before I, here we are. So what's the probability of surviving the second year given one survived the first year? Well, in this case, everybody, those who started 2014 through 2017, remained in the study for at least 2 years, right? Because they passed the first year and the second year. Those who came in, however, those who came in 2018 were only followed 1 year. So they were not here for the second year. So we have to eliminate those individuals from our calculation. So although we have 270 individuals who survived 1 year, right? We have 270 individuals who have survived 1 year. Of those 270, only 200 were here through the second year, right? Because these 70 Malgies, they weren't here for more than 1 year, right? I had this tennis coach who used to use the weirdest language, and he used to call people Malgies. I have no idea why, so I like to say that once in a while. So of these 270, these 70 individuals here were only here for 1 year, right? They didn't follow up to the second year. So so our total at the end of the second year going to the third year is going to be 270 minus these 70 individuals, right? So let's go to my calculations here. So So those that survive 2 years is going to be 93. So this is the start of at the end of the first year, we had 270. 70 of those people weren't followed for an additional year. We had 93 surviving. So 93 divided by 270 minus 70 is 93 divided by 200, which is 0.465. So now we want to know how many survive 3 years. Well, only 3 cohorts, so each individual that's in a specific grouping, like those who started 2014, 2015, and 2016, those are considered cohorts of individuals. There were 3 cohorts that were followed for 3 years. 2 of them weren't, like this one was only followed for 2 years, and the 2018 one was only followed for 1 year. So we had 93 individuals at the start of the second year. However, 18 of those Malgies were not followed into the third year because they were only here for 2 years. So our denominator in this calculation is going to be, because again we're dealing with those who survived for 3 years, would be 93 minus 18, because again those 18 people weren't followed for 3 years. Now we know 39 individuals survived, so our last calculation will be 39 divided by 93 minus 18, which is 0.52. Finally, okay, so here's the interesting thing. So this calculation is the probability of surviving 2 years given you survived 1 year. Okay, so you have a 47% chance of surviving 2 years given you survived 1 year. You have a 52%, right? 0.52 times 100 is 52. You have a 52% chance of surviving 3 years given you survived 2 years. If I ask you, as I did here, what's the probability of surviving 3 years? That means you had to survive the first year, and the second year given you survived the first year, and the third year given you survived those other 2 years. So that probability, because there's an and, is a product, using the multiplication rule, is a product of these 3 probabilities. So we just multiply those together, and we get 0.152 or 15.2%. So the probability of surviving 3 years is 15.2%. Notice that's different from the probability of surviving year 3 given you survived year 2, which is a lot higher, 52%. So this is how you calculate, or how you conclude that first problem. Let's go to the second problem. So now we're going to do a similar problem, and actually it's basically the same problem, but I'm including missing data. So at times we have people who are lost to follow-up, right? Lost to follow-up. That means people come into a study and for some reason they withdraw. Like they may get bored or they may move away and we can't follow them anymore. So in most longitudinal studies are studies that have a baseline and then people are followed over time. We also call them panel studies. We lose people to follow up. So this is the case here. So we're losing people year to year. All right, so here's our problem. So we want to calculate the probability. We can find the actual problem here. We want to calculate the probability of surviving 3 years. That's what we want to do. I think the problem is, it's just the probability of surviving 3 years. And we're giving this really, really nice matrix here that we're going to work with. So the question is, what's the probability of surviving the first year? So we have 400 individuals at the start who are alive at the start of treatment. Then we have 178 individuals who die. And we have no withdrawals during this first year. Everybody's there. This is great. So our effective number exposed to the risk of dying is 400 because we didn't lose anybody. The probability of dying, or the proportion who died during this interval, is going to be 178 divided by 400, or 0.465. 0.445. Now, either you die or you don't die. These are mutually exclusive events, right? So if one occurs, the other one cannot occur. And there are only two possible outcomes in this scenario. Either you die or you don't die. So our sample space has only two events, death or survival. So the probability of all possible mutually exclusive events has to sum to 1. So the probability of surviving or not dying is 1 minus the probability of dying, and the probability of dying is 0.445, so 1 minus that is 0.555. So that's our probability of surviving 1 year. Okay, so let's go on to calculate the rest of these, because now when we go to the second year, we start with 400 minus 178, which I have here. So we have 400 minus 178, right? Because we lost those 178 individuals, right? So we're starting with 400 minus 178, which is 222 individuals, right? Now, here's the interesting issue. We start with 222 individuals. Now, we lose in this interval going from year 1 to year 2, we lose 40 individuals for whatever reason. They're gone. They're not in the study anymore. But we don't know when they're leaving. So we want to account for their participation in the study. So we have, HALVE, have this value. So we'll account for them, give them like a weighting of 1/2. So we'll say they're here for half the time. But we have to subtract them. We don't want to subtract all 40 from this start value of 222, because we'll assume that these individuals were here half time. So we're going to subtract 20 out of this. We're going to divide this number by 2. So 40 divided by 2 is 20, and 222 minus 20 is 202. So 202 is our effective number exposed to the risk of dying during the interval. So now, that's our new denominator, and we had 85 individuals who died during this interval. So we're going to divide 85 by 202 to get our proportion dying, and to get our proportion surviving. Again, surviving and dying are mutually exclusive, and they have to sum to the value of 1, because probability has to equal 1. The probability distribution of any sample space has to come up to 1. So we have 1 minus 85 divided by 202, which equals 0.579. Okay, so that's our probability of surviving 2 years, given one survived the first year. Now, the last thing we have to calculate is the probability of surviving 3 years, given one survived 2 years. So where do we start here? Okay, at the end of year 2, this is interesting now. At the end of year 2, we didn't have 202 people, because remember, we split this 40 in half, right? So we had 222 people minus 85, because 85 died and 40 left. So if we run this here, let me just clear this because I just did this. We have 222 minus 85 minus 40 gives us 97 individuals. 97 individuals. Okay, so let me recap how I got that, right? Because we started the second year with 222 people. We had 85 deaths and we had 40 withdrawals. Now, when we calculated the effect of being exposed to the risk of dying, remember we halved this value here of withdrawals. But now that the year is over, we don't have to have it anymore. So we subtract the total 40. That's how we get 97. Now, to to calculate the probability of dying in the third year, we need to know how many people were exposed to dying. So we need the affected number exposed to the risk of dying during this interval. And again, we're going to have this value here. So half of 24 is 12. So we're going to go 97. So let me clear that. We go 97 minus 12. We get 85 individuals. 85 individuals who are exposed to the risk of dying. To get the probability that, or the proportion who died, we just divide the number of deaths in the interval. It's 21 by 85. So let me go back to my calculations here. So we have 21 divided by 85, and we subtract that from 1 to get the probability of surviving, or the proportion surviving. Our survival rate was 0.753. All right, so the probability of surviving 1 year was 0.555. The probability of surviving the second year, given you survived the first year, is 0.579. And the probability of surviving the third year, given you survived the second year, is 0.753. So it's very likely that you'll survive the third year, given you survived the second year. However, that's not the question I asked. I asked what's the probability of surviving 3 years. That means you must have survived the first year and the second year, given you survived the first year, and the third year, given you survived the prior 2 years. So that's an and situation. So what's the probability for surviving the first year and the second and the third, right? So that's an and situation. That means multiplication. If we multiply these three together, we get 0.242. So there's a 24% chance of surviving 3 years, which is a lot lower than the probability of surviving the third year, given you survive the second. So there's a benefit if you keep on surviving. All right, let's go to the last one. The last one here. So this is what we call the Kaplan-Meier method. So in this case, instead of using a time frame where we're talking about years, surviving 1 year or 2 years, that's a very discrete point in time. What we do is we count. What we do is we do our counting based on when any person dies, or when any person does not survive. Let me put it this way, because we use this Kaplan-Meier method, or we use survival analysis for all types of situations. We use it a lot in substance abuse research. So for instance, in a treatment for substance abuse, such as smoking, people smoke and we'd like them to quit. But what happens is over time people relapse, so they don't survive, right? Surviving would mean to remain quit. Relapse would be a failure to survive. So we can use the same method whether we're talking about death from some disease or abstinence or lack of abstinence from a drug. So this is what we're going to do here. So let's start the situation. Let me see what the situation is. Suppose we're testing a new smoking cessation program for 10 heavy smokers. You're interested in tracking abstinence using the Kaplan-Meier method. The data are presented in Table 1. In addition to the relapse points, there were 3 individuals lost to follow-up. And you always have to know when they were lost, because these individuals, unfortunately, act as if somebody who died, right? When they're lost, they're lost. So you got to do your best to keep them in the study. Lost to follow-up occurred as follows. 1 participant moved out of town at 14 months, and 2 individuals could no longer be located for tracking at 22 months. Complete the empty cells in Table 1. All right. So here we are. We started with 10. Let's see. What did we start with? 10 individuals, right? First person relapsed at 6 months. So what's the probability of a person surviving 6 months? Well, we have 1 relapse, so we divide 1 by 10 to get the proportion who relapsed. So this is 0.10. The proportion who remained abstinent, well, abstinence and relapse are mutually exclusive, so it's 1 minus the proportion who relapsed. So 1 minus 0.10 is 0.9. And in this case, the cumulative proportion who remained abstinent is 0.9, and we can see this in my calculations here. Okay. right? It's 0.10. That's the probability of, well, that's the probability of relapsing, actually, right? That's the probability of relapsing. Is that right? Yes. So I had this wrong. So, it's okay. I can calculate it. What I did was I did something wrong there. So I'll just calculate it as we go on. You have to forgive me. Okay. So we have here 0.9, right? 0.9. With 0.10, 0.10. This is actually probably better that I did it this way. So this is 0.9, 0.90. All right. So now it said, according to this, it said that the first person moved out of town at 14 months. So between 6 and 12 months, nothing happened. So the number of individuals abstinent at the start of this new period, or by 12 months when the second person relapsed, was 10 minus 1 or 9, right? So if we want to know the proportion of relapse, we take column 3 divided by column 2. So we have 1 divided by 9. So let's just do that here. We have 1 divided by 9, which is really simple. It's 0.1111 goes on and on. 0.111. So the proportion who remained abstinent in that second period was 1 minus this, right? So we got 1 minus 0.111 and gives us 0.889, right? 0.889. So the cumulative proportion who remained abstinent, so that means they were abstinent at 6 months and 12 months. That's a product of these two, right? So we get this, right? This is the second proportion, 0.889 times the first, which is 0.9, and we get 0.8001. So 0.8001. Right? Oh, 0.8 I said. All right. So now during this second time, this third period here, right, from 12 to 18 months, we lost another person because we said we lost one person at 14 months. So now we have 9 minus 1 is 8 minus the person lost to follow-up is 7, right? So what's the proportion who relapsed here? It's one of those 7. So let's go and calculate that. We get 1 divided by 7 equals 0.143. 0.143. So the proportion who remained abstinent is 1 minus the proportion who relapsed. So we have 1 minus 0.143, 0.857. So 0.857. 0.857. Now, if we want to know the proportion who remained abstinent through 18 months, would be the product of these three, right? Because they had to remain abstinent at the first at 6 months, 12 months, and 18 months. We can multiply the 3, or I can take this value and multiply it times 0.8001 since I already did this multiplication. So I get 0.857 times 0.8001, and I get 0.686. 0.686. You can see over time, fewer and fewer people remain abstinent. And finally, let's see what we had at the last point. And 2 individuals could no longer be located for tracking at 22 months. So that's between these two. So we lost 2 more people, plus we lost the person who relapsed. So 7 minus 1 is 6, minus the 2 who couldn't be located anymore gives us 4. that's 0.25. Oops. So 1 minus 0.25 is 0.75. So you notice if you survive through 18 months, the probability of surviving or remaining abstinent at 24 months is pretty high. But the probability of remaining abstinent across all 4 of these time points is going to be a lot smaller. So what we'd have to do to find it out, or to calculate it, is 0.9 times 0.889 times 0.857 times 0.75, or 0.75 times 0.686. So let's do that. So we got 0.686 times 0.75, and we got 0.514. 0.514. Okay, so what does this say? The probability of surviving or remaining abstinent through 24 months is 51%. So we can multiply this by 100 and get 51%. So if you survive, you didn't relapse at 18 months, the probability of remaining abstinent for 24 months is pretty high. So these are 2 different values. We're really interested in this value here. All right? I hope this helped. And I'm sorry for all the noise, but hey, that's where I live. I live in a noisy area. Thank you. Bye.